All right, good afternoon, everybody. I'm going to get this set up to see what we're looking at today. I hope things are going well for you. I hope people can catch this video either while I'm on here or sometime soon. Catch up on what we're looking at with logarithms and wrapping up this chapter 6 material. I'll try to go through some examples on this today of the main ideas from the second part of chapter 6. And we got to catch up. So let me get this turned around and taking a look at the piece of paper here. Feel free to chime in with some questions as we go along. All right. So this is what we got to take a look at. First, big reminder is exam times. I had a few options of exam times in Monday's announcement. I've heard from some people and gotten them written down for Thursday night time and some for the Friday daytime, Friday afternoon time. You gotta let me know which one of those you want to take the test, and I'm gonna email the test out to the people in those time slots. So, looking at either Thursday evening starting at 8 p.m. or Friday starting at 12 o'clock. I've got a 3-hour time window there, so these are open book tests. You're going to have 3 hours to work on them. It's going to be plenty of time, but you're going to work on them during that time and email them back to me. But let me know which one of those time slots works. Or if something's up with both of those times, we can work something out. But get in touch with me one way or the other. We're looking at the rest of logarithms and how they work now. There's a few rules for rewriting logarithms that I kind of call them taking apart and putting together. They get different terminology for that, but that's basically what's happening with rewriting logarithms. And that allows us to be able to solve some equations there, being able to do that. And then we have a change of base formula to go over. So if you have a logarithm with some weird base, you can turn it into something that you can actually do on a regular calculator using regular logarithm. So we will look at the basics on that. Now, there is stuff in Module 11 in the Lumen course about the logarithmic graphs. We're not really going too far down that road, but I want to remind people you've got a one-to-one function if you have some kind of exponential like y equals 4 to the x. Then you've got a graph that is a one-to-one function. This would go through when x is 0, you would get 1. And when x is 1, you would get y equals 4. So it would go through those 2 points. And we've talked about the shape of these things. So the exponential functions look like this. They keep going this way. This is a nice one-to-one function. We hit each value exactly once. So this does have an inverse. And the inverse of this function would be what we call the log base 4 of x. We're not really going to graph these things, but this is the kind of expression that we're working with now, the logarithm expression. Seeing how they work. And that going to enable us to solve some equations where there's no way to get x by itself at all. Right? If we start off with an exponential thing where the unknown is part of the exponent, like even as simple as 3 to the x equals 20. We don't have any regular algebraic way to get x by itself, right? You can't get this out of the exponent using regular operations of algebra because it's 3 to that power. So we have to rewrite that into logarithm form to get the x by itself, and that's what happens when we change that over to logarithm form, the equivalent expression there. This is the input and output for an exponential. So this inverse function would be log base 3. And the input here is what was the output there. And the output here is what was the input there. So that gets x by itself. Great, we got x equals log base 3 of 20. I still don't know how to calculate that thing and end up with a numerical value. We're going to need another thing on that, but I am able to get x by itself using that change of form. So we'll work on some of those. Some of those are in the homework here, which I'm going to do some of during this time here to try to cover some examples of the skills that you need for that homework assignment. One other reminder while I'm doing this early stuff is if you're using the XYZ homework site, I have several signed up for that and some that have been working through the chapter in there. It is chapter 6 in there, using some of the examples and doing some of the practice problems in there. That's good practice for the homework. You do have to put in, if you're working along in there and you haven't done it yet, you have to put in the XYZ 2020 code. That's what they gave us to give you free access for the rest of the semester. So if your account there is saying something about a grace period, then you got signed up, but you got to put the code in to extend that to use for the rest of the semester. And hopefully that works out. If not, let me know. But that should give everybody access to keep using that through the rest of this course. Now, calculating something like that is one of our goals that we got to get to. That's where we're going to need that change of base formula. I think I'm going to go ahead and work with that now, and we'll come back to taking apart and putting together with the more complicated stuff in a minute here. But as long as we've got this sitting here, might as well finish off how we would actually go to calculate that. Because most calculators have a log button, but it's just regular log, which is log base 10. And you have a natural log button, which is log base E. This isn't either of those things. So I got to do something different with this. I'm going to rewrite it using the change of base formula. I'm going to explain where this comes down, but where this thing comes from, because it's a good illustration of the properties right here. But basically, I can calculate this using regular log of 20. If I just take the regular log of 20 and then divide by the log of the base that I'm trying to get rid of here. So this had a weird base 3. I want to get rid of that. I can change it to regular log of 20. I just have to divide the value by the log of 3, and that'll still be the same expression. So that's going to give me the actual solution to that. So let me see what that comes out to on the calculator here. I have one handy. I think this is readable on here. So notice I've got a log button. It's just regular log, which is base 10. It doesn't even say that, but it's common log is base 10. So log of 20 is going to be some weird number. 1 point something. Log of, since this is base 10, the log of 10 would be 1. So the log of 20 is a little bit more than 1. But I need to do that divided by the log of 3. So I'm going to just take that answer divided by log of 3. It comes out to 2.72. So x is approximately 2.7, actually rounds to 2.73. That's the approximate value of that thing. That's the solution to this equation up here now. But if I do 3 to the 2.73, that's the one that's supposed to come out to 20. 3 to the third is 27, so this would be a little less than that. That sounds right. We can kind of check our answer using regular exponent button. 3 exponent 2.73 is going to be now close to 20, right? We did a little rounding there, so that's the value. It's very close to 20. So that's the approximate solution to that. And there wouldn't really be a way to get that number without using logarithms or some form. The reason this is equal to this is I can actually explain it somewhat if I start from this form. We started with 3 to the x equals 20. And instead of rewriting that using log base 3, if I just do this regular log of both sides, if 3 to the x equals 20, then the log of 3 to the x should be the same as the log of 20. And whatever that function is, I can do it to both sides. That's the regular base 10 log is what I'm using. And the fact is, when I have the log of a power, you can rewrite this thing. This is one of the rules that we're getting used to, is that this is the same as log base 3 times x. X times log of 3. Any exponent like this can be turned into a multiple. So that didn't change anything. That's still equal to the log of 20, and that's how I know that x can be calculated doing log of 20 divided by log of 3. It just comes back to that property of logarithms, which is part of my take apart and put together rules. So I want to kind of narrate those a little bit. I have a couple of people like listening now. Maybe some other people can catch this later. I want to do some examples of how these take apart and put together rules work. And this is one of them, this thing with exponents. So I'm going to refer to some of the homework exercises in here. Hopefully you've tried some of these out. If not, you will be in the next few days. The homework from the rest of chapter 6 here is due next Monday, but we've got to take the test on this stuff now. So jump into this in the next couple of days. We're going to take the test Thursday night or Friday. So try these homeworks out before then, and you should see pretty similar questions on your test. And I'm doing some from 6.5 right now. I'm going to do examples from 6.5. This is number 60. I'm going to work through this and kind of write down what the rules are that are in play here that we're working with. The take apart rules. The instructions here say to expand each of the following expressions. So we're told to expand the expression, and that's kind of a weird word. In regular polynomials, expanded means you're breaking it up into a whole bunch of terms. And it means the same thing here. Expanding, it means writing it in this expanded form where we have a whole bunch of terms. So it's the same, it's what I call taking apart logarithms. We're going to start with one complicated logarithm expression, and we're going to take it apart into a bunch of simple ones. That's what the word expand means. So for number 60, it tells us to do natural log of 10e to the 4t. It's a good idea when you have any kind of log to use the container here. This is the input into your logarithm. It's not written that way in the book, but we want to be able to think of this the right way. All of that is the input into that logarithm function, and that's what we want to take apart. When this is multiplication inside here, whenever two things are multiplied inside of that logarithm, we can take it apart into the two pieces here, the 10 piece and the e to the 4t piece. And it's the natural log of this one plus the natural log of this one. So anytime there's multiplication in here, it becomes addition when you expand it or break it apart. So this is this property that says any kind of logarithm, if you have multiplication in there, it can be rewritten separately. It's the log of A and the log of B. But you're adding them. So multiplication inside the log turns into addition out here. Remember, these are exponents. They really represent exponents. So multiplying means adding exponents. It's tied to that property. Okay, it looks a little weird with this. Takes some getting used to, but that's how the expanding rule works. Or if you're putting together, you can use this the other way to turn stuff into multiplying. Anyway, I can go a little bit further with this one because of my exponent rule that I had before. Anytime there's an exponent rule, form of multiplication, it turns into a multiple out here. So the natural log of 10 stays there. This is the same as 4t times the natural log of e. Any power can be turned into a multiple of the logarithm using this property. It says the log of any power can be turned into a multiple of the log. That's always true with any exponent, even strange looking exponents. We're going to have one more rule to add to that list for the take apart rules, but don't need it right here. Now, since the natural log is base e, is the log base e, this is the log base e of e. That's a nice number right here. This is going to be just natural log of e is just 1, because we're talking about log base e of e to the 1. That's asking what exponent do I put on e to get e to the 1? And the answer to that question is just 1. So that's because the base matched up with the base right there. These are inverse functions. The natural log is the inverse of the exponential base e. So these are kind of canceling each other out and leaving just the 1. They're inverse functions. That's one way. So I can simplify this and say it's just the natural log of 10 plus 4t times 1 is still 4t. So that's a little nicer way to write it. That's an expanded form of that one because we separated it out into terms. Now this is something you could actually calculate if you wanted to write the number down, but it's really not going to make any difference there. It's unlike terms anyway, so I'm just going to leave it as it's written right there. And I'm going to work one in the other direction where you're using what I call it, the same rules, but you're using them to put stuff together. We got one other thing to add to the list right there. Before I go on, I'm going to go ahead and write it down. The properties here. Similar to the multiplication one, but if this is division inside here, it's the same as having the b to the minus 1 power, so we're just going to get a minus when we break that up. If we separate that out, it's going to turn into subtraction of the logs. Division is subtracting the exponents, so we get an expression like that. The division turns into subtraction that way. So that'll help us to expand. If our original expression involved division, we could break it up that way. That's actually what these things were invented for originally. Logarithms were invented because multiplying and dividing numbers was difficult, and adding and subtracting numbers is a lot easier. In the pre-calculator days, it was a lot easier to add and subtract stuff. So people would do multiplication by using logarithms and separating it out so they could actually work with addition and subtraction of the numbers and then figure out the answers that way. It made things easier for a big number of calculations in the pre-calculator days. We don't need them for that anymore. We do kind of need them to solve certain kinds of equations, and the class of functions that we get out of there ends up being very important one in calculus also, and in some other applications. But while I'm in 6.5, I'm also going to work with number 84 here. This is one that's later in the homework. And the instructions now are to write as a single logarithm. So we're going the other direction with this. This is putting together stuff. A single logarithm would be putting together stuff. So we're going to take longer expression and put it back into a single expression, single logarithm instead. So we're using the same rules, which I have written up here, and try to keep them on the screen. We're using these same properties, but we're going to be using them to put stuff together instead. The operations are going to change that way. And for number 84, we're working with this expression 4 natural log of a minus 3 natural log of b minus 5 natural log of c. Now I copied that down the way it's written in the book, but I'm going to throw the containers in here because this looks like it's multiplied by something the way it's written now, and it's not. It's the input into the natural log. These are all inputs into that function. Doesn't make any sense to write ln unless we have something that we're doing the natural log of. So it's got to have an input. I'm going to write it that way so I can keep track of that. But I want a single logarithm, so I just want one ln instead of all these separate pieces. And we're going to use these same properties to do that. The 4 and the 3 and the 5 are multiples here. So I'm going to use this rule first that says that multiple can be rewritten as an exponent. We're going to put it back in that form. So this turns into the natural log of a to the 4th. And this turns into the natural log of b to the 3rd. And this turns into the natural log of c to the 5th. Got that put together a little bit, but now I still have 3 logarithms. The subtraction here has to be put together. So I'm going to use this rule in this direction. When I have log minus log, I can turn it into the log of this. I'm going to use the division in here. So doing this piece, this becomes the natural log of this divided by that, a to the 4th divided by b to the 3rd. I'm just doing one piece at a time here. See, just doing one piece at a time, but now this divided by that. So I have the natural log of a to the 4th over b cubed divided by c to the 5th, but the way that the fractions are dividing by c to the 5th, I can just put it in the denominator. So I could just write in this as a to the 4th divided by b cubed c to the 5th. Put that together a little nicer. That's the single logarithm way of writing that thing. That's going to make it easier to solve certain kinds of equations with this stuff. That we're actually not going down that road. So I'm not going to take time on solving logarithm equations. We're not going that far with this thing. We're going to do an application of these things, you know.
I know, you like to feed people, don't you? Only a little bit.
So a familiar place where you use something that's actually a logarithm without thinking about it is doing what they call pH. So I'm not a chemistry person, but I know about pH a little bit, that it determines how acid or base a substance is. So we're going to look a little bit at pH. Get this pH of a substance, where you can calculate what determines how acid or base something is really the concentration of hydrogen ions. It's going to look like this. This H plus is the chemistry symbol for the hydrogen ions that are in there. How much of that it has determines how acid or base it is. But the concentrations are tiny little numbers. They're like 0.000 something, or even smaller than that. They're tiny little values. So instead of using the actual concentration for the scale, they wanted a mathematical tool that'll take this and convert it to some nice numbers that are easier to work with. And since they're tiny, tiny, tiny little values, the log of them ends up negative because the concentration is less than 100%. So, of course, the log of it would be negative. So we're going to take the concentration of that, which is written this way. Take the log of it, it gives us a negative number. They didn't want negative numbers to use for the scale either, so they made them positive. They take the opposite of that. That's the relationship that's going on there. So if you know the pH of something, you can figure out what that concentration is, or vice versa. If they if you test your vinegar using some kind of test strips, you might find out that it has a pH of something like 5.75. I think they come out around 7. The pH, I think 7 is kind of neutral. 5.75 is something you might get from a substance like that. And if this is the pH for something, then we could find the actual concentration in there and calculate it. So 5.75 is minus log of this thing. This is just fancy chemistry symbol for the concentration of ions in there, but this is my unknown. That's what I'm trying to solve for. I want to get that by itself. So I want to get rid of the negative in the log here. Getting rid of the negative, I can just move it to a second. Do the opposite of both sides here to take care of that. But getting rid of a logarithm, that's not a thing that I can get rid of using regular division or multiplication or something. It's a function. I have to get rid of it by switching over to exponential form. This is really log base 10. So when I switch over to exponential form, I have exponent base 10. What was the output before becomes the input here. And what was the input before becomes the output here. So that is how I get this unknown by itself. The value is 10 to the minus 5.75. That's a tiny little number. It's the actual concentration of hydrogen ions in your bottle of vinegar. That's the case. So I can get the actual number if you calculate them. It's so small it might stay in scientific notation. I don't know what we're doing. 10 exponent negative 5.75. Calculation that we want to do for that. So I can do that with the regular exponent button here. And the value is coming out in scientific notation there. That e to the minus 6 doesn't spread. This is so small, it's written in scientific notation. It's basically 1.778 times 10 to the minus 6. Scientific notation might use a little e on your calculator too, or there might be a little 10 there, depending on how your calculator displays it. That's exponent negative 6. That's the scientific notation for that concentration. It's so small that it comes out in scientific notation usually. And if you think that's terribly inconvenient, well, that's true. That's why they use pH instead. So instead of having to deal with numbers like that, they can deal with numbers like 5.75. It's nicer to work with. So that's why they use that kind of scale on it. It's a logarithmic scale. We want to be able to work with that. So if you're given the pH of something, it takes a little work to solve for the concentration of it, but you can turn this around and get that concentration using exponent key. If it's the other way around, if you know what the concentration is, like if we're starting with, here's the one from number 89. If you're starting with orange juice and you know that the concentration of hydrogen ions in there is 6.50 times 10 to the minus 4. You can find the pH using that same expression. The pH is minus or negative log of the concentration. So if you know the concentration, you know the input, you're just doing this calculation then. minus log of 6.50 times 10 to the minus 4. And that you can calculate directly. We don't have to do anything to get it by itself because this formula is already written with the pH by itself. So here we go. We just have to do minus log of, and I still like the containers in there, 6.50 times 10 to the negative 4 has to all be on the input of that logarithm. So the parentheses help with that. It's minus log of that concentration. And the calculator says that's equal to 3.187 approximately. So that's rounded, but that's what the pH of this is. So that's one application. That's something you should see a little bit of, especially those of you that have to go on and take chemistry. Good for you. You'll see a lot of pH stuff in there at some point. And using those tools is important. Calculator's set up to do log base 10 and to do exponent base 10. So both of those things are easy to do with the calculator, but you have to get used to the notation and the setup and how to work it out a little bit. So we try to introduce that a little bit when we're going through the properties here. We're not going to do the logarithm equations, but we are going to use logarithms to solve equations. I did a simpler one already. I'm going to do a couple of these exponential equations that are a little bit more complicated from 6.6. I'm going to work a couple of these examples similar to the homework exercises. Spend a little more time on it. So this is the last part of what we do in this chapter. It'll be the last part of your homework, 6.6. I'm going to do number 24 from here. Think this thing through a little bit. It says solve each exponential equation. Use a calculator to write the answer in decimal form. So we're going to get this thing written in a form where we can calculate it and round it off. Okay, so it's probably not going to come out to a super nice number, but we want an approximate solution at least. And the equation for number 24 is 7 to the 4x plus 3 equals 200. So the unknown that I'm trying to solve for, I'm solving for x, but x is up there in the exponent. There's no nice way to get that out except for changing to logarithm form. So I'm going to have to change this to logarithm form and work it out to solve for x. So I'm ready to rewrite that as log base 7. But let me think about that first before I do that. Let me think about some powers of 7, because the question is, what power up here, or what is x to make the power up here work out so that you get 200 from this? 7 to the 1 equals 7. 7 squared equals 49. 7 to the third is 49 times 7, which comes out 343. So somewhere in between there, 7 to the something comes out 200. That would have to be in there somewhere. We're going to find an x. Makes that exponent come out somewhere in between there. Doesn't take that big a number to get results like this out of an exponential. So we don't need a very big value of x for this. We'll see how it comes out. To get started algebraically, getting x by itself, I have to get it out of the exponent. This whole thing is the exponent. I have to rewrite that using logs. So if that's exponential base 7, then this becomes a log base 7. And rewriting this between these two forms is key to get used to it. But the output that we had here becomes the input of this. And the input that we had into our exponential becomes the output, or whatever was your exponent is by itself now. And that's allowing us to solve for x. because we got that out of the exponent now, where we can use regular algebra to get x by itself. Now the log base 7 of 200 looks weird. I want to just go ahead and calculate what that is and write it down as a decimal because I'm looking for that form anyway. And if I go to the calculator, there's no log base 7 on here. That's where I need that change of base formula that we did, because I don't know where, I don't know the log base 7 of anything. I've got to do that using change of base formula to use the regular log button. That's all I have for that. So the change of base formula tells me if I want log weird base of some number, I just do the regular log of the number, but I divide that result by the log of the old base, or the weird base. So I have to do log of 200, regular log of 200, take that answer divided by the log of the old base, there, 7. That comes out 2.722. I'm going to round it to the thousandths place. It would round to 723, actually. 2.723 is 4x plus 3. That's the number, thinking back here, that would have worked to get to 200. It turns out to be between 2 and 3, this nice value between 2 and 3. That's what the exponent would have to be. But now we can solve for x using regular calculations here. So subtract 3 from both sides. Comes out negative. Divide by 4. Negative. We'll catch up on this in the calculator. Divided by 4. Round that to the thousandth. I got negative 0.069. The solution on that one. That's the x value that would work in that equation. Check the answer. That's a nice thing to be able to do. It's a good thing about solving equations is you can check the answer. And we can do exponential base 7 with that. So looking at what my original equation was, it's telling me that 7 to the 4x plus 3. So I need 4 times this x value plus 3. That is supposed to come out to 200. Why didn't I get 200? I think that's the right number. What did I do wrong on this? Positive. Oh, because I entered it wrong. It's 0.069. See, I just did the calculation wrong here. What's that? 7 exponent 4 times negative 0.069. That's pretty important to the place value right there. Plus 3. Very close to 200. So that actually worked out like it should. If you enter it right, it works out like it should. So that checks out and gives me a value very close to 200. These things might look a little different on different calculators, so you want to get used to that. You'd be able to do the calculations in the homework and on the test, so make sure that you're getting things that come out right. And one way to do that is to check the answers. If it's an equation, you can check the answers and make sure they actually work. Good practice with that. That's a pretty good overview of the skills you got to be able to do on this. I just kind of did one of each kind of thing, kind of flying through this. Everything in chapter 6 is going to be on this exam. So the stuff that the homework that I've seen already from the early part of chapter 6 went pretty well. I got back to people with comments on that. So I'm keeping up with the homework when you get it submitted. So here's what I got to have people do. I hope this gets out to the rest of the people. We got a couple now, but hope this gets to everybody else. But you, of course, need to turn in all the chapter 6 homework. Came in 2 sets. Second set's not technically due until Monday, but it would be a good idea to turn it in early and get some feedback on that before you take the test. Let me know by email your exam time. Supposed to take this test either Thursday evening or Friday afternoon. Specifics are there in that earlier announcement, but let me know if one of those times is good. Look through the announcements page, you'll see the time slots there that I wanted to work with. Now, if you're looking at your situation and you can't sit down and take that test during one of those time slots, well, we'll figure out a different time slot, but let me know one way or the other. Let me know if you need some other time on what would work for you. We're all trying to make this work. So if neither of those can be done, let me know. And any questions that come up as you're trying to do this homework, get the questions to me either on email or Blackboard discussion, and I'll get back to people. I'm trying to keep up with that. So the questions to me, any of those that you have trouble with, there's some strange things to get used to. So get a little practice. The nice thing about the Lumen homework and the XYZ homework is those aren't really homework problems, but the nice thing about the practice that's in there is it'll let you know if you're right as you go along. You can see examples and it'll let you know when you're getting the right answers. So you get some feedback from that right away. But if there's some of those you can't get them to come out right, let me know. I'll get some practice in there, and I'll get this chapter 6 test ready to send out some of y'all tomorrow evening. All right, keep in touch. Signing off.